Welcome. Today, we'll take a deep dive into supervised learning, a fundamental concept in machine learning. Supervised learning is all about teaching machines using labeled data, where the correct answers are already known. This approach allows algorithms to learn from examples and make predictions or decisions based on new, unseen data. In this video, we'll walk through the entire process, from understanding the basics to seeing real-world examples and finally exploring how supervised learning is applied in various industries. Let's get started by first understanding what supervised learning really means. Supervised learning is a type of machine learning where the model is trained on a labeled dataset. This means that each training example is paired with an output label. The algorithm learns to map inputs to the correct output, essentially learning from examples. Think of it as a teacher supervising the learning process, providing the correct answers during training. The goal is for the model to generalize from the training data so it can accurately predict outcomes for new, unseen data. This is different from unsupervised learning, where no labels are provided. Let's break down the key components of supervised learning. First, we have the input data, which consists of features or attributes that describe each example. Next, there are the labels, which are the correct answers or outcomes for each example. The model is the algorithm that learns the relationship between the inputs and the labels. Finally, there's the training process, where the model adjusts its parameters to minimize errors and improve accuracy. Understanding these components is crucial before we move on to practical examples. Supervised learning can be divided into two main types: classification and regression. In classification, the goal is to predict a category or class label, such as determining if an email is spam or not. In regression, the aim is to predict a continuous value, like forecasting house prices. Both types use labeled data, but the nature of their outputs differs. Understanding the distinction between classification and regression helps in choosing the right approach for a given problem. Let's look at a classic example: email spam detection. Here, the input data consists of features like the sender's address, subject line, and email content. The label is whether the email is spam or not. The model is trained on thousands of labeled emails, learning patterns that distinguish spam from legitimate messages. Once trained, the model can analyze new emails and predict whether they are spam, helping users keep their inboxes clean. Another popular example is predicting house prices. In this case, the input features might include the size of the house, number of bedrooms, location, and age of the property. The label is the actual price of the house. The model learns from historical data, identifying how each feature affects the price. After training, it can estimate the price of a new house based on its features, making it a valuable tool for real estate professionals. For training a supervised learning model, it's essential to prepare the data. This involves collecting relevant data, cleaning it to remove errors or inconsistencies, and transforming it into a suitable format. Sometimes, features need to be scaled or encoded, especially if they are categorical. Proper data preparation ensures that the model receives high-quality input, which is crucial for achieving accurate predictions. Common practice in supervised learning is to split the dataset into training and testing sets. The training set is used to teach the model, while the testing set evaluates its performance on unseen data. This split helps prevent overfitting, where a model performs well on training data but poorly on new data. Typically, about 70–80% of the data is used for training and the rest for testing. There are many algorithms available for supervised learning, each with its strengths and weaknesses. Common models include linear regression, logistic regression, decision trees, support vector machines, and neural networks. The choice of model depends on the problem type, data size, and desired accuracy. Experimenting with different models and tuning their parameters is often necessary to achieve the best results. Training is the process where the model learns from the labeled data. During training, the algorithm adjusts its internal parameters to minimize the difference between its predictions and the actual labels. This is done using optimization techniques like gradient descent. The model iteratively improves its accuracy as it processes more data, eventually becoming capable of making reliable predictions. After training, it's important to evaluate how well the model performs on the testing set. Common metrics for classification tasks include accuracy, precision, recall, and F1 score. For regression tasks, metrics like mean squared error and R-squared are used. Evaluating performance helps identify if the model is ready for deployment or needs further improvement. Overfitting occurs when a model learns the training data too well, including its noise and outliers, resulting in poor performance on new data. Techniques like cross-validation, regularization, and pruning can help prevent overfitting. It's important to strike a balance between fitting the training data and maintaining the ability to generalize to unseen data. Hyperparameters are settings that control the learning process, such as learning rate, number of layers, or tree depth. Tuning these hyperparameters can significantly impact model performance. Techniques like grid search and random search are commonly used to find the optimal combination of hyperparameters for a given model and dataset. Cross-validation is a technique used to assess how well a model generalizes to new data. The dataset is divided into several folds, and the model is trained and tested on different combinations of these folds. This provides a more reliable estimate of model performance and helps in selecting the best model configuration. Feature engineering involves creating new features or modifying existing ones to improve model performance. This can include combining features, extracting useful information, or transforming data into a more suitable format. Good feature engineering can make a significant difference, sometimes even more than choosing a complex model. Not all features are equally important. Feature selection is the process of identifying and using only the most relevant features for training. This reduces complexity, speeds up training, and can improve model accuracy. Techniques like correlation analysis and recursive feature elimination are commonly used for feature selection. Once a supervised learning model is trained and evaluated, it can be deployed into production. Deployment means integrating the model into real-world applications, such as websites, mobile apps, or business systems. The model then makes predictions on new data, providing valuable insights or automating decisions. After deployment, it's important to monitor the model's performance over time. Data can change, and models may become less accurate, a phenomenon known as model drift. Regular maintenance, retraining with new data, and performance checks ensure that the model continues to deliver reliable results. Supervised learning is used in many real-world applications. Examples include medical diagnosis, credit scoring, speech recognition, and image classification. In each case, labeled data is used to train models that can make accurate predictions, improving efficiency and decision-making across industries. Healthcare supervised learning models are trained on patient data with known diagnoses. These models can then predict diseases or recommend treatments for new patients based on their symptoms and medical history. This helps doctors make more informed decisions and can lead to better patient outcomes. Banks and financial institutions use supervised learning to assess credit risk. By analyzing historical data on borrowers and their repayment behavior, models can predict the likelihood of default for new applicants. This enables more accurate and fair lending decisions, reducing financial risk. Supervised learning powers speech recognition systems, such as virtual assistants. These models are trained on audio recordings paired with text transcripts. Over time, the model learns to convert spoken language into written text, enabling hands-free interaction with devices and services. Image classification. Supervised learning models are trained on labeled images. For example, a model might learn to distinguish between cats and dogs by analyzing thousands of labeled photos. Once trained, it can accurately classify new images, making it useful for organizing photo libraries or powering visual search engines. Supervised learning offers several advantages. It provides clear guidance during training, often resulting in high accuracy. The approach is well suited for problems where labeled data is available, and it's relatively straightforward to interpret and evaluate model performance. These strengths make supervised learning a popular choice for many practical applications. Despite its strengths, supervised learning has limitations. It requires large amounts of labeled data, which can be expensive and time-consuming to obtain. The model's performance is also limited by the quality and diversity of the training data. Additionally, supervised learning may not perform well on tasks where labels are unavailable or ambiguous. Like supervised learning, unsupervised learning works with unlabeled data. It seeks to find patterns or groupings within the data without explicit guidance. While supervised learning excels at prediction, unsupervised learning is better for discovering hidden structures or relationships. Understanding the difference helps in choosing the right approach for your problem. Semi-supervised learning combines elements of both supervised and unsupervised learning. It uses a small amount of labeled data along with a large amount of unlabeled data. This approach can improve performance when labeled data is scarce, leveraging the strengths of both methods for better results. Linear regression is one of the simplest supervised learning algorithms. It models the relationship between input features and a continuous output by fitting a straight line to the data. Linear regression is widely used for tasks like predicting sales, prices, or trends, thanks to its simplicity and interpretability. Logistic regression is used for classification problems where the output is a category or class. Despite its name, it's a classification algorithm, not a regression one. Logistic regression estimates the probability that an input belongs to a particular class, making it useful for tasks like spam detection or medical diagnosis. Decision trees are versatile supervised learning algorithms that can handle both classification and regression tasks. They work by splitting the data into branches based on feature values, creating a tree-like structure. Decision trees are easy to interpret and visualize, making them popular for many applications. Support vector machines, or SVMs, are powerful supervised learning models used for classification and regression. SVMs find the optimal boundary that separates different classes in the data. They are effective in high-dimensional spaces and can handle complex, nonlinear relationships using kernel tricks. Neural networks are inspired by the human brain and consist of layers of interconnected nodes. They are capable of learning complex patterns and are widely used in image recognition, natural language processing, and more. Neural networks require large amounts of data and computational power, but can achieve state-of-the-art performance. Ensemble methods combine multiple models to improve prediction accuracy. Techniques like bagging, boosting, and random forests are popular ensemble approaches. By aggregating the predictions of several models, ensemble methods can reduce errors and increase robustness, often outperforming individual models. Labeling data for supervised learning can be challenging. It often requires expert knowledge, especially in fields like medicine or law. Labeling large datasets is time-consuming and can introduce errors if not done carefully. Crowdsourcing and automated labeling tools are sometimes used to speed up the process, but quality control remains essential. Supervised learning models can inherit biases present in the training data. It's important to ensure that data is representative and free from discrimination. Ethical considerations include fairness, transparency, and accountability, especially when models are used in sensitive areas like hiring or law enforcement. Generalization refers to a model's ability to perform well on new, unseen data. Techniques like data augmentation, regularization, and dropout can help improve generalization. Ensuring diverse and representative training data is also key to building robust models that work well in real-world scenarios. Automated machine learning, or AutoML, simplifies the process of building supervised learning models. AutoML tools can automatically select algorithms, tune hyperparameters, and evaluate performance, making machine learning accessible to non-experts and speeding up development cycles. Businesses use supervised learning to optimize operations, personalize marketing, and enhance customer experiences. For example, recommendation systems suggest products based on past purchases, while fraud detection models identify suspicious transactions. These applications drive efficiency and competitive advantage. In scientific research, supervised learning helps analyze large datasets, identify patterns, and make predictions. Applications range from genomics to climate modeling, where models assist researchers in uncovering new insights and accelerating discoveries. Supervised learning is part of our daily lives, often without us realizing it. From voice assistants and spam filters to personalized recommendations on streaming platforms, these models work behind the scenes to make technology smarter and more user-friendly. Despite its widespread use, supervised learning faces challenges such as data scarcity, labeling costs, and the risk of overfitting. Addressing these challenges requires careful data management, regular model evaluation, and the use of advanced techniques to ensure reliable performance. The future of supervised learning looks promising, with ongoing research focused on reducing the need for labeled data, improving model interpretability, and making models more robust. Advances in transfer learning and self-supervised learning are expanding the possibilities, enabling smarter and more adaptable AI systems. Let's recap what we've learned. Supervised learning uses labeled data to train models for prediction and classification. It involves data preparation, model selection, training, evaluation, and deployment. While it offers high accuracy and clear guidance, it also requires quality labeled data and careful management to avoid pitfalls like overfitting. For successful supervised learning projects, start with clear objectives and gather high-quality labeled data. Experiment with different models and tune hyperparameters for optimal performance. Regularly evaluate and update your models to keep them accurate and relevant as new data becomes available. Supervised learning is a powerful tool that drives many modern technologies. By understanding its principles and best practices, you can harness its potential to solve real-world problems. Continue exploring machine learning, experiment with datasets, and stay updated with the latest advancements to make the most of supervised learning in your projects.